Welcome to the experiment 6 of EEE 342 Introduction to Communication Engineering Laboratory. In this experiment, we are going to conduct simulations on amplitude shifting. There are basically two variants of amplitude shifting that we are going to discuss in this experiment. The first one is the natural amplitude shifting. Another one is a special variant of amplitude shifting, which is on-off key. Basically, we are going to start off our experiment with on-off key. So I have given the detailed lecture and theoretical aspects of this on-off keying and amplitude shifting in my theory class videos, or the videos of EEE 341, and I have attached those videos in this experiment of EEE 342 as well. You can find those videos in the experiment section of PACS, where you will get all the necessary videos from the theory lectures and also this video. So if you are starting off the experiment straight away with this video, I'm not going to recommend doing that. Go back, watch the theory lectures so that you get a deep insight of what is ASK and what is OOK, and then come back and start off the simulation. So without any delay, I'm going to start off the simulation right now. So I have loaded my Simulink already. By this time you already know how to load Simulink and how to take components from Simulink and build a model. So I will straight away go into building our model. So first of all, we're going to build an on-off keying system. In the on-off keying, just a brief overview what is on-off keying. Let me load my workspace. Okay, so basically in the case of on-off keying, we have a digital sequence, which is a sequence of 1 and 0. You already know. Let's say our sequence is 1 0 1 1 0. So if I draw this sequence, so this will be something like this: 1 0 1 1 0. So if I modulate this signal with a carrier signal of high frequency, let's say a cos wave, so there's basically no extra portion over here. Okay, so I have a cos wave as my carrier. So this is my carrier cos wave. My cosine carrier. So in the on-off keying, my output signal will be this very carrier for ones, and nothing for 0. Again carrier for ones, and then again nothing for 0. So how can we achieve this signal using these two signals? This is very straightforward basically, because you can just simply multiply them. Because if you have 1 here and 0 here, and if you just multiply this signal with this, then for this region the input signal is 1. So basically the cos carrier will be multiplied by 1 and it will remain as it is. For this portion, however, the input signal is 0. So if you multiply this signal with whatever signal, it will be 0 in the output. And in this region it is again 1 all the way for 2 bits, and if you multiply it with the cos carrier, the output will be same as the cos wave, and again it is 0 for this portion, and if you multiply this with our cos carrier, then it will be 0 again. So simple, very simple. You have to drag a sine block and you have to create this digital sequence. So this is a new thing which will be introduced in this experiment, so I will go into detail of this in my Simulink. Let's go back to it. So here I will be taking components. I will need a sine wave, of course. I will get that in my sources. So you can see in the sources block, I will get a sine wave. Here is my sine wave, so I will get that. Okay, I'm giving it here. So I need to generate that random binary sequence, right? So you can get that. Let me search for generator. So we will use this Bernoulli binary generator for generating that digital sequence. You will find it under the communication systems toolbox. So you can just search for generator here and then find out this Bernoulli binary generator, or you can just go from communication systems toolbox and find that. So in the communication systems toolbox, you can find this Bernoulli binary generator. Okay, so let me drag this. Okay, so now I have my generator as well. So let's start generating. Okay, so in this window, you will need to make up some changes. The first one is the source of initial seed. It is set to auto. Don't set it to auto. Go to parameter, and then you will get a new window here for setting the initial seed. Now this initial seed is used for generating the same random sequence every time, because it's a random generator. So every time you simulate this, if you set the source of initial seed to auto, then it will automatically generate a random sequence for you. You will not have any control over that. Maybe you are experimenting with some sequence right now. Let's say it is 1010, and you are simulating again, and that sequence gets changed to, let's say, 1110. So it's a bit problematic. So we will try to have some control over it. That's why we will set it to parameter, and then set whatever number you wish to. I will set 61. So if I set 61 here, every time I simulate this whole circuit, I will get the same random sequence. If you set 62 here, maybe you will get a different random sequence. Okay, there is no like real connection between the numbers and the sequence. Just set it to whatever number you like. I am setting 61. Okay, now sample time. Sample time means how many time will each sample take, or let's say there are ones and zeros, how many time will each 1 or 0 take. I will set it to 0.1. So each bit will take 0.1 second right now. Samples per frame, you can take it to 1. Okay. So now I will set my simulation time to 1 second. Why is that? So in my Bernoulli generator, there will be 10 samples in 1 second. Why is that? Because my whole simulation time is 1 second. And in my Bernoulli generator, each sample is taking 0.1 second. So if you just do some basic calculations, some basic division, you will see that in 1 second time there will be 10 samples. So it's just simple division. The total time is 1 second divided by sample time, which is 0.1 second. So the division result is 10. So there will be 10 samples in the 1 second time frame. That's good. So let's check this out with our scope, just to make sure we're on the same page. So here's my scope. I will just connect this and run my simulation. Simulation is done. Let's see. Oops. So here you can see there are 10 samples. 1 0 1 0 1 0 1 1 0 0. So 1 2 3 4 5 6 7 8 9 10. As expected, there are 10 samples, and it's a combination of ones and zeros. So what happens if you change the initial seed? I change the initial seed to 43, let's say, and simulate this once again. So now you are seeing a different version of this random sequence. It's random. So now it's 0 1 0 0 0 1 1 1 0 1. Okay, you can use whatever version you like. I will be sticking to 61. I just basically love this sequence. That's it. Nothing special about 61. This sequence is very uniform and easy to understand the experiment. So I'm using this one. You can choose whatever you want. Okay, so I'm done with my Bernoulli generator. Now let's get back to my sine wave. Okay, so I will be choosing a frequency amplitude. Let's keep the amplitude to 1. Bias to 0. Frequency, let's choose the frequency of 100 Hertz. You need to put 2 pi in front because the frequency is in radians per second and 100 is in hertz. So you need to multiply it with the 2 pi to set it to radians per second. So that's there. And let's choose cos wave. So 90-degree phase shift. You can choose sine wave also. It's basically the same thing, just a phase shift. And sampling time. This sampling time I have already told about this sampling time in previous experiments. So you basically know how to choose this. Choose a very small value for it. I am choosing 0.0001. Okay. Okay. So let's check this sine wave out. So this is my cos wave. It doesn't look pretty well, but that's okay. Let's shorten the simulation time a bit and check whether it is actually a sine wave. Yes, it is a cos wave. Maybe I can increase the simulation time a bit more. Okay, so it's a cos wave. Yes, it's a perfect cos wave. So let's start our simulation. You can choose sine wave also, that doesn't matter. Okay, so as per our theoretical discussion, we need to multiply these two outputs and set it to scope. That's basically it. So let me increase the number of ports of this scope. Let's set 3 ports here. 3 ports for 2 inputs and 1 output. Okay, so that's basically it. And we also need a product block. Just search for product. Okay. So make sure it's element wise product. So this is element wise. Okay. So first input, second input, and the output goes here. Let's keep a track of the sine wave. Let's keep a track of the Bernoulli generator as well. So now we can see the whole picture over here. Let me set the simulation time back to 1 second. So all the 3 waves are shown in the same window. I want to see them separately. So go into settings. There is a drag down button here. So click that and click this axis option. So set 3 graphs. Okay, so here it is. First one is our cos carrier. The second one is basically the digital sequence 10 10 10 10 10 10 10 1100. The both are multiplied, and then there is our on-off keying output signal. So the modulation is done. So this signal is our digital sequence, and we are modulating it with a cos carrier of 100 Hz frequency, and then the whole thing turns to an on-off keying signal like this, and that is transmitted via any method to a larger distance. Okay, so that's basically our modulation. Now we will do the demodulation part. So for doing the demodulation part, it's necessary to understand what's the frequency spectrum of the whole signal. Okay, so let's bring an analyzer here, spectrum analyzer. So let's just search for analyzer. This is a spectrum analyzer. I will choose that one. Okay, so now I will need to analyze the spectrum of the sine wave. Let's see, the frequency was 100 Hz, so we already can expect something readily over here. The frequency of our cos wave was 100 Hz, so in the frequency domain we can expect 2 impulse, one in 100 Hz and another one is in minus 100 Hz. So we can expect this. So let's see if it's the case actually. It's taking some time to simulate. Okay. The spectrum analyzer requires 1536 samples to update the display. Okay, so you can see the spectrum here. It's not very easy to visualize. Let's see what we can do with it. So change the type to RMS. We'll give a better view. Okay. So now we can see there are two sharp peaks at 100. The axis is basically in kilohertz. So 100 hertz means basically 0.1 kilohertz. So at 0.1 you can see a sharp peak and another peak at minus 0.1. So this is basically what we expected. Okay. Now let's keep a track of what our Bernoulli generator's spectrum looks like. Okay. So this will not simulate at first try. Okay, this will not simulate, I guess. Yes, this will not simulate because we do not have sufficient amount of samples, because our sampling time was 0.1 and we only had 10 samples, but we need a lot of samples to actually plot the spectrum. So we need to increase the sampling, decrease the sampling time. Let's say 0.001. Okay. Set the time to 2. These are just temporary changes. We will get back to original settings once we visualize the spectrum. Okay, so this is our spectrum. You can notice something, that most of the significant frequency components are close to zero frequency. You will see a very sharp peak at 0, and then the frequency is gradually decreasing in both sides. But it's not 0, because a complex signal like the signal we have seen for our random sequence has a very large number of sine or cos waves in it. If we expand it in Fourier series or Fourier series, so there we will see a large number of sine and cos waves of different frequencies. But the most important thing is that as the frequency increases, its coefficient also decreases. That means it's contributing less to the original signal. The main contribution comes from, you can see, from frequency components which are very close to 0. So this is a very important thing we wanna care about. So now what happens? What happens if we let's say this is our spectrum of random sequence. This is the spectrum of our random sequence. I'm not very good at drawing. So it's something like this. So this is our original mass spectrum. Whatever random sequence you choose, the spectrum will be something like this. They will be different, but you will not actually experience the change with naked eye. I mean, they will be different. Basically, they will be different, but the change will not be drastic, because it's random and always the frequency spectrum will look something like this. The majority portion of the frequency spectrum will be concentrated at this low frequency region. Now we are modulating with our cos carrier. So cos carrier has a frequency spectrum like this. One sharp peak at 100 Hz, another sharp peak at 100 Hz. So now we are modulating this spectrum with this cos wave. So we already know that modulating in time domain means shifting this original spectrum to the frequency of the cos wave and the negative of it. So this whole spectrum will be shifted to 100 and minus 100. So this is my 100, this is my minus 100. It should be something like this. And the amplitude of this spectrum will be half of original, so now it will be A by 2. But the spectrum will be shifted to 100 Hz and minus 100 Hz. So that is basically the spectrum of our modulated signal. So now what will happen if we try to demodulate the signal, and we will be using coherent detection. So we will modulate this again with this signal, or in the time domain we will basically multiply this signal with this cause wave again. So what will happen? The same thing will happen again. This whole spectrum will be shifted to 100 and minus 100. So now what will happen? Let's choose a different color. Let's say this is 0, this is 100, this is 100, this is 200, this is minus 200, and this is minus 100. Okay, so when we will modulate this signal, let's say this is M-F. When we will modulate this M-F with this cos carrier again, the whole signal will be shifted to 100 and minus 100. So now the center frequency is 0, so the center frequency will be shifted to 100. So this 100 will be shifted to 200. So something like this. And again the amplitude will be 1/4 of the original, because it is dragged down to A by 2 here, and when we modulate it again, it will be A by 4 right here. Okay, and another part, the minus 100 will be at 0. Okay, so we have done the first part. So what happened here is this whole spectrum is shifted to 100 Hz. How is that? Let's just go over it once again. The center frequency was 0, and one frequency component was at 100. So if the center was 0, it was in 100. If I shift the center to 100, it will be at 200, because this gap will be 100 always from center. So the whole spectrum is shifted to 100. The center is shifted from 0 to 100. So this component goes from 100 to 200, and this component goes from minus 100 to 0. Okay. And the amplitudes are A by 4. A by 4. Now this whole spectrum will be again shifted to minus 100. So now the center is minus 100. So this component will go to minus 200, because it is minus 100 with respect to 0 center. Now the center is 0 minus, center is minus 100. So this component will go to minus 200. Let me draw it over here. Okay, that's it. And another component that will come from 100 will go to 0, because it's 100 with respect to 0 center. When my center is shifted to minus 100, this component will go to 0. So same thing again. So these two will be added, and there will be a higher frequency spectrum here. So I can change it and draw the sum of the yellow and the blue spectrum components here. It's basically A by 2. These are A by 4s. Okay. So now this is the multiplication of this message or the modulated signal and the cause carrier in the frequency domain, of course. Now if we just use a slow pass filter here, then we will get our original spectrum. So there will be some change in the original amplitude, but that will not affect much. So that's our setup. So we have got our modulated signal. We will need to multiply it with our cause carrier and then use a low pass filter to filter out. So let's do this. We don't need the spectrum analyzer right now. So let's just delete that. Okay, and change the settings of the Bernoulli generator as previous. 0.1 and 1 here. Let's just simulate it once again to check whether everything's alright. Okay, so this is our original carrier, our random binary sequence, and this is our modulated signal. Okay, so now we need another product block, because we need to multiply the modulated signal with the carrier again. So let's just put it here. So one input will come from this carrier, another input will be the output of this product block. Done. So this is basically our multiplication of carrier and the modulator signal. So let's just use a digital filter to filter out. So you can see our let's say our filter will have some cutoff frequency somewhere between 0 to 100 because it will be spread out. I have just drawn a random shape here, but it will be spread out. So if you choose a very small cutoff frequency, it will not work. Let me just demonstrate it. In original practice, there will be also some more components here and there, it will be spread out a lot. So we will choose a cutoff frequency somewhere around. There will be two frequencies. One is f pass and f stop. You can see at certain point it starts to go down, and at some point it becomes like 0. So this is basically our f pass, and this is basically our f stop. So we can choose that this f pass close to 0. Let's say this will be, let's say, 10, and this f stop can be something like 90. It's on the negative side. In the positive side it will be the same. It's 10 and it's, let's say, 90. So let's choose our digital filter. This is our digital filter. Now we will put it in front of the multiplier block. So the multiplication of the cos carrier and the output modulated signal is now passed to the digital filter. We will run the scope. Let's just copy it, paste it. Okay, so I will need to check the Bernoulli sequence as well. Okay. So let's set the parameters for the digital filter. So it's a very complicated dialog box. Don't be intimidated by it. So low pass filter we will need. So low pass filter is there. We need a FIR filter. Equal is okay. Set this filter order to minimum order. You don't want to set the order by yourself. Just set it to minimum order. Set the frequency axis to Hertz because it will be easy to visualize. Now set this sampling frequency equal to the sampling frequency of the sine wave. So it was, sampling time was 0.0001 second. So sampling frequency would be 1 over this value. It will be 10,000. So I'm choosing this frequency to be 10,000. Otherwise it will give a warning. Now what is f pass and f stop? As I have mentioned previously, that this is the filter we want to deploy, and f pass is something like 10 and f stop is something like 90. And 90, or even you can use more than that. Let's just do the experiment with this one. Let's see. Click this design filter button. Let's keep the rest of the settings as it is. It will take some time to design the filter. So this is our filter. The frequency axis is in kilohertz. So the f pass is set to 0.1. So you can just see it. It's actually hidden somewhere here. And f stop is 90. So it will be 0.09. So 0.09 is somewhere over here, so that's fine. This is our filter that we are going to use, and the filter order is something that is important. So the filter order is 317. This will affect our simulation. So let's see how it goes. Okay, so the second input was kept blank, so there is nothing in the second box. Sorry, nothing in the second box. The first one is the output of the digital filter, and this is our digital input sequence. So you can see a close resemblance between these two signals. Obviously there will be some imperfection, because when we are filtering out, we are leaving many frequency components behind. So as you were seeing in the original frequency spectrum, that the input spectrum was something like this. So there was a lot of components going on. Whenever you will use a filter, this will go on and on. Whenever you will use a filter, you will leave some components behind. So whatever frequency you use for f pass and f stop, you will need to leave some components behind, because you cannot go over 200, right? If you go closer to 200 for f stop, it will start capturing this component as well. We don't want this component. So our f pass and f stop needs to be somewhere between let's say 10 to 150. You can use this as f pass and use this f stop. But if you go beyond 150, then you will start capturing the components from this sideband. You don't want that. Okay, so let's just increase the f stop a bit. Let's increase it to 150. Let's see how it goes. Okay, let's see how it goes. Is there an improvement at all? Yes, there is some sort of improvement. Let's just increase it to, let's say, 250 and see how it goes. Now we should start capturing some components from the sideband. So yes, you can see we have started capturing some components from the sidebands at 200 Hz. So we don't want that. We don't want this ripple over here. So we will need to keep our f-stop less than 200 and preferably closer to 100. So let's choose it as one. Let's choose it as 50. What happens if we choose it as 50? Keep an eye on this filter order. So if we choose this f-stop to be 50, our filter order is 633, which is huge, and the more the filter order, the more the delay. So let's just simulate it. Okay, so you can see we have lost a lot of components. So this estimated signal is somewhat relevant to this input sequence, but there are a lot of smooth edges where we need sharp edges actually in these regions. Sharp edges means high frequency. As we are setting our f-stop less, closer to 50, then we will lose our high frequency components and it will become smooth. For sharp edges, we need high frequency components. So when we choose our f-stop to be 50, we are leaving a lot of high frequency components behind, and we don't want that. So we need to increase the f-stop much higher. Not like 250, but something around 100 to 150 would be great. Now we need another component, that is compare, because we want to take our decision. We want to take our decision based on this signal. So we need to compare this signal with a constant. So let's choose the compare block. Compare to a constant. Put it over here. Okay. So this goes to the output of the filter, and this goes to the scope. Now, if you just check this signal out, the signal is moving somewhere between 0 to let's say 0.6, I guess. We want to set a threshold at, let's say, 0.2. If our input signal is greater than 0.2, we will set it to 1. and if our input is less than 0.2, we will set it to 0. So let's choose this threshold as 0.2. You can choose 0.1 as well, whatever is accurate, and we will choose a greater than operator. Okay, so let's check. Okay, so this was the input sequence, and when we chose the constant to be 0.2, threshold to be 0.2, whenever my signal is greater than 0.2, I will get a 1, and whenever my signal is less than 0.2, I will get a 0. You can see that. So this is actually very similar or very close to this input binary sequence, but there is a delay to it. You can see this signal is delayed basically. This delay will because of two reasons. The first one is the filter order. The higher the filter order, the more the delay. The higher the filter order, the more the delay. If you choose this f pass to be, let's say, 1 instead of 10, if you choose it to be 1, or let's say 5, now the filter order is 633. I am choosing my f pass to be 5. My filter order has increased. Let's decrease this f stop a bit more. The lower the gap between f pass and f stop, the higher the order. So the order will increase even more now. So the filter order is 723 right now. Let's see how the simulation goes in this case. Okay, so instantly the order increases. Okay, so you need to keep this order as low as you can. Let's choose this f pass. Let's keep the f pass at 5, and let's choose the f stop to be 120. Now you will get a much lower order, and as we are taking 120 as our f stop, we will incorporate much higher frequency components, and the signal will be sharper right now. Let's see if we can catch some sharp edges right now. Similar to this. Yes, see this signal? This is much sharper. This region is much steep compared to the previous one. So yes, if you increase the f stop within certain limit, you will get a sharper signal, and the delay will be less compared to the previous cases. Okay, so that's it. That is basically all for our OOK. We have done our modulation and demodulation. So that's all. Now let's go to ASK. Okay, so I will not build the circuit for ASK. I have already built that. Let's just copy and paste it. This is a similar circuit, but now we will have two different signals for 1 and 0. So let me just give a short overview right here. So in the case of ASK, we will again have one input binary sequence, which will be a combination of 1s and 0s. Let's say it's 1, 1, 0, 1, 0, 1. So 1, 1, 0, 1, 0, 1. Okay. And we again have our carrier, but now we will need two different carriers. One carrier for bit 1 and second carrier for bit 0. And what will be the difference between these two carriers? These two carriers will have same frequency but different amplitudes. So let's say our first carrier signal is C1, and it is 5 cos 2 pi into 100t. And we have another carrier, this is for 1, which is 2 cos 2 pi into 100t. This is for 0. So we have two different carriers for two different signals, and the main difference between them is this amplitudes. The frequency are absolutely same. So how can we make that work? We will need to design some circuit, and the output of that circuit will be something like this. So let's draw some axes. let's just amplify it a bit. So 1, 1, 0, 1, 0, and 1. Now let's draw the scales. Okay, so this is 1. So for this one we will have the amplitude of 5 and the frequency of 100, of course. And this is also 1, so we will have the frequency of amplitude of 5 again, frequency of 100. But now this bit is 0, so we will have an amplitude of 2. So you can see the frequency is still 100, but the amplitude is 2. And then we will need 5 again. And 2 again. And 5 again. So that's basically it. So we need this as our modulated signal. 2 different amplitudes for different bits, 1s and 0s. So how can we do that? So here, this is our Bernoulli generator, same as previous. We are multiplying this with our cos carrier. Let's see what the cos carrier over here is. Amplitude is 5, frequency is 100, phase is 90. So this is a cos wave, and sampling time is same as before. So that's done. So what will happen in the output? Let's just try to visualize this first. This was my original input, and my output is the multiplication of this input sequence and a cos carrier of amplitude 5. So this will be 5, all the way up to this. Then it will be 0 because the input is 0 over here. So if you multiply it with whatever signal, it will be 0. Again 5. Zero over here, and again 5. So this is nothing but an OOK signal with amplitude 5, right? Now we will invert this input sequence. What does inverting mean? Inverting means ones will become zeros and zeros will become ones. So 0, 0, 1, 0, 1, 0. How can we do that? If you subtract the input bits from here from 1, you will get this. 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0. So when you try to invert this binary sequence, you will just need to subtract the sequence from 1. So let's draw this one. There's a shortage of space over here. Let me just draw it. Here. So this will be something like 0, 0, 1, 0, 0, 1, 0, 1, 0. Okay, so now we will multiply this signal with another carrier, but that will have a different amplitude of 2. So for that case, so this is the output. Let me just erase this one. Just remember this yellow signal. We will use it later. So multiply it with another cos carrier, which has an amplitude of 2. So 0 over here, so nothing. Then here it will be 2. Again 0. Again it will be 2. again 0. So the yellow signal was something like this, 5 over here, zero over here, 5 over here, 0 over here, 5 over here. So if you just add these yellow and red signals, you will get your ASK signal, the full ASK signal. That's all. So we are doing it over here. This is our first sine wave, which has an amplitude of 5 and frequency of 100 and phase of 90. Now we are negating this Bernoulli, the output of this Bernoulli binary generator. Here is a subtractor block here, and we are subtracting this output of Bernoulli binary generator, the random binary sequence, from 1. So this is our inverted input, and we are multiplying it with another sine carrier, and for that case we have amplitude of 2 and the frequency of 100, which is same as before, phase of 90, and a sampling time, which is same as before again. Now we will need to add the signals and we will get our modulator signal. So let's just have a look at it. So here you go. This is your input Bernoulli binary generator. So 1 0 1 0 1 0 1 1 0 0. So you will see that this is my modulated signal, and the modulated signal has a higher amplitude when the input sequence is 1, and when the input peak is 0, it has a lower amplitude. Okay, so that's all for our modulation. Now we'll go back to demodulation. Demodulation is basically same as before. We need to modulate the signal, modulated signal, with one of the carriers. You can choose whatever carrier you want. I have chosen this high amplitude carrier. You can choose the low amplitude carrier as well. So let's see what is in the filter, digital filter. So again we have similar sort of parameters. We have low pass filter, we have Faraday ripple filter. The sampling frequency is 10,000, and we have an f pass of 1 and f stop of 95. We can choose 5 over here and 120 over here as before. No problem. Okay, so let's just simulate it once again. Oh, okay, there was only 3 scopes. Okay, so this is the output of the digital filter. Here you can see the signal is varying from 4 to, let's say, 8.5. So the lowest value is 4 over here and the highest is 8.5. So you need to pick a threshold between 4 and 8.5. Okay, so I have chosen 7. You can choose 6 as well. So when I'm doing the threshold thing, this is converted to this output. This is the output of the compared to constant. So this is our demodulator signal. You can see the demodulator signal is a very close resemblance of our input Bernoulli binary sequence. There is a delay, of course, and you can minimize the delay if you carefully choose the f stop, f pass, and the threshold. That's basically all for ASK and OOK. In the ideal case, there is also some noise mixed with the modulated signal when it is demodulated again. So in the report you will do some of that as well. So that's all for this experiment. See you again in the next experiment. Thank you.